In this chapter, I'll discuss Bayes' rule. Mendenhall gives one section, 3.7, on Bayes' rule, and he does one example. I think if you go through this, then you'll be able to understand his example a little bit better. Also, it's nice to have these examples that I've written here. A lot of people in literature will talk about Bayes' rule, but they never really go through the steps, and it's nice to see the steps. First, we have to derive Bayes' rule, and we do that. We're going to start with the multiplication rule, which, as you know, is related to and, or intersection. Okay. Event A is going to be the one that we're trying to assess. D is going to be the data that we've acquired. So I want to use that terminology. Mendenhall uses A and E. E for data, but I'll use D for data just because I think that makes more sense. Okay, let's start with the general multiplication rule for events A and D happening together. D meaning the data that it's acquired. We're looking at the probability that that data would have even occurred. So the probability of A and D is the probability of D alone times the probability of A given that D has occurred. Or we can write this rule as the probability of A times the probability of D occurring given that A has already occurred. And our goal is to find the probability of A given D. In other words, what is the probability this event is going to happen given that I already saw some data? So it's like, you're watching somebody play dice. What's to roll some dice? What's the probability that I'm going to get a 6 given that I've seen this game go on for a while and I have seen either other combinations show up or this particular show up way too many times. And that's what we're talking about. What is the probability of A given that I've seen this data happen? Okay, let me review Bayes' rule for a minute. That was several lectures ago, so it's easy to forget. Okay, in Bayes' rule for probability, you start with a prior probability. And that's usually the same thing that the frequentist would have derived just based on the number of times the event occurs divided by the number in the sample space. So you start with this prior guess, which is as though you're looking at the situation as though it were an ideal situation. Then you watch what happens for a while, and that's the new data that you get. And from this you calculate, or you rather update your probability. So we started with the probability of A doing something like this. Then D occurs, and now we're going to change. Now we want to know the probability of A given that D has happened. So this is our updated, it's called a posterior probability. You can just look at it as though it's an updated probability. So that's where we're going. This is what we want to do, and we start with the general multiplication rule, and we write it like this. You can write it this way, or you can write it this way. Okay, now assuming the probability of D is not 0, then I can divide both sides of the equation by D. Let's just do that one right there, and then isolate it. So now I have the probability of A given D is the probability of A and D occurring together divided by the probability of D alone. What I've done here is also, I just write the same thing here, but I use the set intersection notation just so that you can get familiar with it. Okay, this doesn't change anything. Now, go look at this situation and write, so now A and B can be written this way. So I expand A and B by using this, and now I have Bayes' rule. So the probability of A given D equals the probability of A, that was your prior probability that you calculated way up here, usually your ideal probability, times the probability that D occurs given that A, probability of getting that data given that A, okay, the truth or the occurrence of A, divided by the probability of D by itself. We're going to do some calculations. The numerator, which looks complicated, is easy. You already have all those numbers. This one takes some work. we'll start with a silly example. Silly examples are always good because they tend to stick in the mind. Maybe this one is not silly enough to stick, but here we go. Let's say that my neighbor said that they're going to buy an animal, and I want to compute the probability that it is a goat. Okay, so say the neighbor was thinking about buying a goat, a cow, a sheep, or a yak, but was sort of leaning towards buying the goat. So I have to form a prior. In this case, there's no formula to drive, to use, in this case. So I'm just going to give an informed guess. I'll say the probability of the goat is 55%. So that's just my prior. And again, this is one criticism of Bayes' rule, because people say, well, how do you compute the prior? Well, there you go. You can also look at different priors and see the outcome too. Now, I get some new information. So this is my data. Just a second here. I'll adjust the slide. So in this notation, the probability, let's say A is the goat. Well, I wrote goat here. It's clearer than writing A. But that's 0.55. Okay. Now the new information, remember we get some new data, and this is D. Here's Bayes' rule. This is what I want. What's the probability that it's a goat given that I know it has a beard? Okay, so it would be the probability of A times the probability of D given A divided by the probability of D by itself. In words, that means what's the probability now that it's a goat given that I know it has a beard? That would be the probability that it was a goat, this is my prior, times the probability that if it's a goat it has a beard, divided by the probability that a beard has occurred. I know this is a lot of words and you have to work through the examples yourself, and there are written lectures. This is all written down. Okay, so let's go back. The numerator. What is the probability it's a goat? I already know that. That was my prior, 0.55. What's the probability that it has a beard given that it's a goat? I'm going to say that all goats have beards, and so that probability is 1. So I know the numerator. Now let's look at the denominator. The way to calculate the denominator, or what the denominator means, is that I have to find the probability that a beard would have occurred in this circumstance with these 4 animals. And the calculation looks like this. The probability that there's a beard in the selected animal is the probability it's a goat times the probability a goat has a beard, plus the probability it's a sheep times the probability that the sheep has a beard. And same for the yak, and same for the other, what the other animal was, cow. Okay. So I know the probability that it was a goat was 0.55. Again, you see how this prior is always kind of lurking here. Now, I need the probability for the other animals. So what's left? 1 minus 0.55 is 0.45. So the probability of those other animals added together is 0.45. Let me say they're all equally likely, so I'll divide by 3 and say the probability for each of the other animals is 0.15. And that way, when I add up all these probabilities, I'll get 1, which is what I should get. And let's say that only the yak has a beard. So the probability a cow has a beard, a sheep has a beard is 0. The probability the yak has a beard is 1. That just, okay. So here's the calculation. Probability it's a goat. Let me clear the screen for a minute. Okay. Probability that it's a goat is 0.55. Probability that if it's a goat it has a beard is 1. Probability it's a sheep is 0.15. Probability that if it's a sheep it has a beard is 0. Probability it's a cow is 0.15 times the probability that if it's a cow it has a beard, that's 0. Probability it's a yak is 0.15 times the probability that if it's a yak it has a beard, which I said was 1. So when I do that multiplication, add it up, I get my denominator 0.69. So that goes here. Remember, I said that was more of a calculation. The numerator I know 0.55 from my prior, and I know this, or I can assign it. Okay, so now the probability that the neighbor bought a goat, given that that animal has a beard, is now about 80%. Previously it was 55%. So that, you see how I had an initial guess, I got some data, and I adjusted my probability, and that's the basis of Bayes' rule. We'll do another one using the dice. So now we have a loaded die. Okay, so we've got 3 dice, and we know that 2 are fair and 1 is loaded. We also know that the loaded die has a probability of rolling a 3 that is 0.4. So that's written right here. Probability that a 3 would be rolled given that it's loaded is 0.4. Okay. For the fair ones, the probability that it's a 3 is 1/6, because that's how it typically was, right? There's no reason to not think that would just be the ideal case. So we're looking for the one that's loaded. All right. So let's say that one of the dice is they're tossed. One is tossed, and it comes up with a 3. So this is highly suspicious, since that was a higher probability there. It's highly suspicious that this one was loaded. Can we calculate that? Okay. So here's how we go. This is Bayes' rule for this case. Probability that this die is loaded, given that it just came up with a 3, equals the probability that it's loaded times the probability that a 3 would have come up on a loaded die, divided by the probability you would have gotten a 3 anyway. Okay, so the numerator is easy again. What's the probability that's loaded? Well, you have 3 dice, and one of them's loaded, so it's a 33% probability, approximately, that you would have just pulled a loaded one out. That's its probability. You've got 3 dice, one of them's loaded. What's the probability that it would have been a 3 given that it's loaded is 0.04, which we knew from up here. So now we have the numerator. Let's go look at the more troublesome denominator. Okay, so what we need in the denominator is a probability we would have seen a 3 anyway. So the way that's computed is the probability that the die was loaded times the probability it would have given you a 3, plus the probability that the die was fair times the probability that the fair one would have given you a 3. Okay, so what's the probability that it was loaded? There was only one was loaded, so that's 0.33. The probability of the fair is 0.67, because either it's loaded or fair, and these two numbers add up to 1. Whoops, this should have been on the new line. Sorry. Let's cash that off. Okay, what's the probability that a loaded dice would give you a 3? That's 0.40, because that was our initial information. What's the probability that a fair die will give you a 3? It's 1/6, so it's 0.167. I add all this up, and this is the probability that I would have gotten a 3 anyway. See, if they were all fair, the probability I would have gotten a 3 anyway would have been 0.167. But now I've got a different situation, because that loaded one would have given me the 3 a little more easily, well, quite a bit more easily than the fair. So here we go. Probability that it's loaded, only 1 in 3 is loaded, that gives me that probability. Probability a loaded dice would have given a 3, 0.40 initial information. What's the probability I would have gotten a 3 anyway? 0.244, 0.54. So look at this. If I don't know anything about these, I just know those dice are laying there, and one's loaded and 2 aren't. So the probability that 1 is loaded is 0.33. Well, more 3's, but okay. Now Now you pick up one of them and you roll, and it turns up to be a 3. So what's the probability that you would have gotten a 3 if this was a loaded dice? It's 0.54. So you see that That extra information, the data of rolling the 3, changed my idea of it being loaded. Why is that written like that? I'm sorry. Probability that's loaded, given that you rolled a 3, that's what I was interested in, sorry, is 0.54. Okay. You see, so this is the extra data, and Bayes' rule allows you to incorporate that extra data to update your probability. Okay, I want to continue this situation, and let's go to part 2 of it. Let's say that the die that just rolled a 3 is rolled again and another 3 shows up. So this is highly suspicious, and we're going to use Bayes' rule again. So here's Bayes' rule again, and this is what we want to find out. What is the probability this die is loaded, considering that a 3 has shown up twice? Right. The numerator is the probability of it being loaded anyway. Here's the probability of the loaded one giving you 2 3s, divided by the probability I would have gotten 2 3s anyway. The numerator, we know, probability it was loaded, there were 3 dice and 1 was loaded, so it's the same thing, 0.33 probability it was loaded. What's the probability that you would have gotten a 3 and a 3 out of this loaded dice? Okay, this is the word and. And is multiplication. Right? So here we're seeing the multiplication rule for and. I didn't write and in here, but I used the comma. Okay, so that would be the probability of doing it once times the probability of it again is 0.16. Okay, now the denominator, we have to find out what's the probability we have gotten, these 2 3s anyway. Well, we could have gotten them from a loaded die or from a fair one. The probability of the loaded occurring is 0.33. Probability of the fair is 0.67. I just computed the probability that the loaded die would turn up 3 twice, and that's 0.16 from here. What's the probability a fair die would give 2 3s? Well, what's the probability for 1 is 0.16 times 0.16, since it doesn't influence each other to do it twice. Here we go, and it's 0.027. I multiply those, add together, and that's what's going to go in the denominator. So here's a calculation. Probability it was loaded, 1 in 3. Probability a loaded dice would give you 2 3s, 0.16. Divided by the probability you would get 2 3s anyway, and the end result is 74.5%. Okay, so let's look at the situation. Before I had any data at all, before I rolled the dice, the probability that it was loaded was 0.33. Then I roll a 3. What's the probability that I got a loaded one given that a 3 has just turned up? That's 0.54. Roll it again and get another 3. You see, and now I've again updated my probability for it. This is a more serious example for Bayes' rule than trying to find a loaded die or looking who's buying goats. This example is from a paper by Jacob Cohen, who is a psychologist, and it's a very interesting example. And when you see this error, you realize that this error is made. There's a conceptual error that's going to show up in a minute, and you will see this error made clinically. But now that you have Bayes' rule and these lectures, you won't make this error. Okay. Let's say there's a test and it's used to diagnose a disease such as schizophrenia. So we're going to start with the probability that a person is schizophrenic, and if there's a 2% is the incidence of schizophrenia in the general population, we'll say the probability of schizophrenia that the person is schizophrenic is 0.02 for the 2%. What's a probability they're not schizophrenic? Well, either in our way of thinking here right now, we have just mutually exclusive categories. So we'll say the probability either you're schizophrenic or not. So the probability of not is 1 minus the 0.02, or 98%. Now let's say that this test is very good. It has a 95% accuracy for making a positive diagnosis. That means if the person is schizophrenic, the test is going to be positive 95% of the time. Seems like a pretty good test. So we can write that in this notation. Let's think about the notation. Probability that the test is positive given that the person is schizophrenic. Okay, that's what that notation is. Remember, this means given. Okay, the vertical line is given. Given the person is schizophrenic, the probability that the test is positive is 95%. Right? Now, again, we're going to use mutually exclusive categories, so either the test is positive or it's negative. So the probability that it's negative in a person with schizophrenia has got to be 1 minus this probability, so it's 0.05. So these add up to 1 because either the test is positive or negative. Alright, let's say it's also 97% accurate when it comes to declaring a person normal. In other words, what's the probability the test will be normal, will be negative, given that the person does not have schizophrenia? That's 97%. So what's the probability it's positive in a person without schizophrenia? That would have to be 0.03. Adding those together, we get 1, which is what's required. So we're talking here, we've got 2 mutually exclusive categories, schizophrenia or not, and the test result either is positive or it's not. So, I mean, this isn't an unusual situation, but now we want to ask the question, what is the probability that if the test comes back positive, the person is schizophrenic? So this is what we want to find out. What's the probability that the person is schizophrenic given that the test is positive? Okay. Well, actually, we want to ask a different question. Positive probability the person is normal given that the test came back positive. At least, yeah. You could ask the other question too. It's still going to be an issue. Okay, we're still going to need Bayes' rule. So the statement of the problem I'm going to show on the next slide. So what we know already is the probability that the test will be positive given that the person is, well, I'll just say normal for purpose of the discussion. Obviously, if you're not schizophrenic, there are many other ways to be abnormal, but I'll just say it normal. Okay, we know that for a normal person, the test will be positive 3% of the time. Now this is the question we want to ask. What's the probability the person's normal given that the test came back positive? If we equate these two, all right, if we say this equals this, then the probability that a person is normal given them that they have a positive test result is 3%. Okay, is this true? The answer is this is not true. This is not necessarily equal, and we have to use Bayes' rule. So I'm going to write out Bayes' rule for this case. I'm just rewriting this. Probability that the person is normal given a positive test result is a probability that the person was normal times the probability that a normal person would have a positive test result divided by the probability I would have gotten a positive anyway. Right. And as usual, the numerator is easy to evaluate. The probability that the person is normal, 0.98, because we had that for schizophrenia, the probability of schizophrenia was 0.02. Okay, so the probability a normal person would have a positive test result is 0.03. We knew that from data about the test. Okay, we knew that. Now the numerator, we have to find all the ways the test can be positive. So that means we have to multiply the fact you would have gotten a positive test out of a normal person times the probability of the person being normal, plus the probability that the test was positive given the person was schizophrenic times the probability the person was schizophrenic. So let's work on that. There was 3% chance that a normal person would have a positive test result. 98% chance a person was normal. A 95% chance that the schizophrenic person would have a positive result times the 2% chance the person was schizophrenic. This is going to go in the denominator. So here is the adjusted or posterior probability that the person is normal given that they're looking at this positive test result. Numerator, probability of being normal, 0.98. Probability that that normal person would have had a positive result, 0.03. Probability we would have gotten a positive result anyway, that's the denominator here. The result is 60.7%. Okay, look at the difference. All right, let me get the pen here. If we make the conceptual error, then there's only a 3% chance that that person is normal. Okay. If we use Bayes' rule and do the problem correctly, all right, we find there's 60.7% chance the person is normal. That's quite a difference. In the lecture on contingency tables, we'll do the same calculation using contingency tables, and that's actually you'll see it's easier to work in a case like this with contingency tables.